Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 7. In this lecture, I'm going to talk about some common distributions. So in this lecture, I'm going to talk about basically three distributions, and really two if you kind of think about it. So the Bernoulli distribution is one, the binomial distribution, which is a distribution based on the Bernoulli distribution, and then I'll talk about the Gaussian or normal distribution, which is a very important one as well. In fact, I think if all the distributions were to get together and nominate a king, it would definitely be the normal distribution. So the Bernoulli distribution is named after Jacob Bernoulli. We've already talked about it before, but let's formalize it a little bit and remind ourselves of some of the notation. So Bernoulli random variable is just a fancy name for a coin flip. So Bernoulli random variable takes values 0 and 1 with probabilities p and 1 minus p, where p is some number between 0 and 1. So the probability mass function for a Bernoulli random variable we've seen before. It's the probability that x takes the specific value 0 or 1, and it's p to the x 1 minus p to the 1 minus x. The mean of a Bernoulli random variable is simply p, and the variance is p times 1 minus p. Facts that we've proven before, but we're just restating them now. And in general, for Bernoulli random variables, if you code a coin flip as a 1 or a head, it's often people call that a success and 0 as a failure. And they tend to do this regardless of whether the classification is actually something that's actually successful. So we might call a person getting side effects from a medication a success in terms of the Bernoulli coin flip. It's just a little bit of odd nomenclature, I guess. We've also already talked about the Bernoulli likelihood function. So if we have x1 to xn are observed data points, so the x1 to xn in this slide are numbers that we recorded, a collection of zeros and ones, then the likelihood is the product, because we're going to model these as independent coin flips, the product of p to the xi, 1 minus p, to the 1 minus xi. We've already talked about this equals p to the summation xi, 1 minus p to the n minus summation xi. So notice again that the likelihood only depends on the sum of the x's, so the total in each x is 0 or 1, so the sum of the x's is just the total number of successes. And then n minus the sum of the x's is the total number of failures. So if you know n and you know the total number of successes, then you know the Bernoulli likelihood. It doesn't matter what order the heads or tails occurred as far as information is contained in the data about the parameter p. Because n is fixed and assumed known, this implies that the sample proportion contains all the relevant information that you need to know about p insofar as the likelihood codifies it. Simply because summation xi and summation xi over n are 1 to 1. You can get from one to the other easily by either multiplying or dividing by n. So the sufficiency result is basically that the proportion of successes is all the relevant information you need to make Bernoulli inference about a parameter. Now, again, this all depends on the model being correct, that you have correctly modeled the data as IID Bernoulli. We also, when we talked about maximum likelihood, we also showed that if you maximize the Bernoulli likelihood over p, then you obtain that p hat, which is summation xi over n, is the maximum likelihood estimator. And here's, we went over an example. So here, just to give you an example of Bernoulli likelihoods and what they look like, imagine if we flipped a coin 4 times. So if we flipped a coin 4 times, there's only 4 possible sufficient statistics that we could obtain. We could get 0 heads, 1 head out of the 4 coin flips, 2 heads out of the 4 coin flips, 3 heads out of the 4 coin flips, or 4 heads out of the 4 coin flips. And here is the 4 possible likelihoods that you could obtain from this experiment. And they're all normalized to have height 1. So here's on the leftmost one is the likelihood you get if you had no heads. The second one, you see it shifted a little bit to the right? And its peak is going to be right at p hat at a quarter, okay? And then if you get 2 heads, then you see that peak, the MLE in this case, is right at 0.5, and the likelihood shifts a little bit to the right. And if you've gotten 3 heads, it shifts a little bit more to the right. And if you've gotten 4 heads, then it shifts closer to 1. Notice, even in the event that you get all tails or all heads, the likelihood is not entirely at 0 or entirely at 1. Right? There's substantial uncertainty, right? The likelihood is correctly codifying the information that it's possible, even if the coin is, say, fair, here's the likelihood point right here, even if the coin is fair, to get 4 consecutive tails. And, it's just much less likely than if the coin is unfair towards some value closer to 0. So the likelihood, it's not entirely shoved up against the vertical line at 0. And it just gets closer and closer to that vertical line as you continue to flip and get tail after tail after tail. Binomial random variables are nothing other than the sum of IID Bernoulli trials. We've seen that the key variable from a Bernoulli experiment is the number of heads. So why don't we just create a random variable that is the number of heads? So in specific, if x1 to xn are IID Bernoulli, then the random variable x, defined as the sum of the individual xi's, is a so-called binomial random variable. And the binomial mass function is just the probability x takes any specific value, is n choose x, p to the x, 1 minus p to the n minus x, where p is the probability from each of the Bernoulli coin flips. Here, the values that x can take are 0 if every single coin flip was a tail, all the way up to n where every single coin flip was a head. Just to remind everyone, the notation n choose x, right, this parentheses n over x, n parentheses, this is n factorial over x factorial n minus x factorial. Here, 0 factorial we're going to treat as 1. And this formula counts the number of ways of selecting x items out of n without replacement, disregarding the order of the items. Okay, so let's consider an example. Imagine I have 10 neckties, and I pick out 3 and put them on my bed, let's say. And I'm not caring about what order on my bed from left to right or something like that. And so 10 choose 3 is the number of different configurations of ties that I could have obtained by picking 3 ties out of my 10 possible. So that's an example. I can't think of any reason why you would want to do this with your neckties, but whatever. So it's very easy, in fact. Certain special cases are very easy. So imagine if I was only picking 1 necktie, right? How many different combinations can I get? Well, intuitively, we know that answer has to be 10, right? Because, there's only 10 possibilities. Well, if you plug into the formula, you have 10 factorial divided by 1 factorial, which is just 1, n minus x factorial, which is 10 minus 1, or 9 factorial. So we have 10 factorial divided by 9 factorial, which is just 10. Okay? Another quite useful one is choose 2. How many ways can you pick 2 things out of n objects? That one seems to come up a lot in my daily life for some reason. And so that's, in this case, would be 10 factorial over 2 factorial, which is just 2, right? 2 times 1. Then divided by 8 factorial, right? So that's 10 times 9 divided by 2. So, at any rate, the general rule is for n choose 2, you just want to take n times n minus 1 over 2. And at any rate, it's one of the ones that it's worthwhile just to memorize the formula for that special case because it seems to pop up a lot. So why is that factor? Why is n choose x the factor out in front of a binomial mass function? So let's now consider the possibility of getting 6 heads out of 10 coin flips from a coin with success probability p. Well, if you account for the order, if you say, what's the probability of getting tail, 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 that's 4 tails, then the remaining are heads, right, in that specific order, right? We know what that probability is. We would just plug into the multivariate Bernoulli mass function obtained by multiplying the Bernoulli mass function for each coin flip in order. And we would get p to the 6th, 1 minus p to the 4th. And as we know, because of the fact that it's only the total number of heads that's sufficient, that if it wasn't just the first 4 coin flips that were tails, if it was the last 4 coin flips that were tails, and the first 6 were heads, then we would get the same number. We'd get p to the 6, 1 minus p to the 4th. And if we had the 4 tails sprinkled in any configuration of the 6 heads, then you will still get the same possible answer, p to the 6, 1 minus p to the 4th. The result is that basically for any collection of instances where you get 6 heads and 4 tails, no matter what the order is, the probability is going to be p to the 6. So what we need is to count how many such configurations there are. Well, in this case, there's 10 flips and 10 positions that could be heads, and we want to know how many different collections of positions we can obtain. And that's just 10 choose 6. It's just exactly the necktie problem, but now we're picking the position of the coin flip that is a head, right? And so in this case, there's 10 choose 6 possible orders of 6 heads and 4 tails. We don't actually have to go through the specific construction of the binomial distribution because I think that's a pretty clear demonstration. That's how you would wind up with the probability of the sum of a collection of 10 Bernoulli random variables being 6, right? You would sum over all the possible ways you could get 6 heads, and it turns out that they all have the same probability, p to the 6, 1 minus p to the 6. So we just need the number of things that go into that sum, and it's pretty clear that it's 10 choose 6. So yeah, we only did this for a specific instance here. I hope you can see that if 10 instead was n, and 6 instead was x, that you would wind up with the same answer. N choose x, p to the x, 1 minus p to the n minus x. So that's the motivation. And you can actually mathematically check that the binomial mass function sums to 1. In fact, it's actually kind of a relatively famous formula, the binomial sum. And so if you, for example, look up on Wikipedia the binomial sum, you'll see that it just exactly illustrates that formula by itself, tells you exactly that the binomial mass function sums to 1, but we're right now just going to trust that we did our calculation right. So let's just go through an example of using the binomial mass function. So suppose you have an intrepid friend that has 8 children, and it turns out that 7 of them are girls and none of them are twins. And so if you're very parsnickety, let's just forget about all the little parsnickety things that you could possibly think about related to this problem, like having twins. So let's just think about the problem in the conceptual way. We're going to think of every child from this family, its gender being a coin flip. And the question is, what's the chance of getting 7 out of 8 children that are girls if it really is the case that every child, their gender is independent from the other children and that there's a 50% probability at each birth of having a girl? And so what's the probability of getting 7 or more? Well, that's the probability of 7 or more is the probability of getting 7 girls out of 8 plus the probability of getting 8 girls out of 8. And so in this case, for the fair coin, it would be 8 choose 7, 0.5 to the 7th, 1 minus 0.5 to the 1. And then 8 choose 8, 0.5 to the 8, 1 minus 0.5 to 0. And, check with your calculator or even better with R, that you can get this number. It's about 4%. This is an example of using the binomial formula. I wanted to mention this particular example because this calculation is an example of a so-called p-value. And a p-value is always the probability under a null hypothesis of getting a result as extreme or more extreme than the one actually obtained. So the logic behind the p-value in this specific instance is that you have this evidence here that you think, wow, 7 girls out of 8 children, that seems pretty odd. Maybe the 50% chance of girls versus boys for this particular family is off for whatever the reason. So the p-value is saying, okay, well, why don't we calculate the probability, if the null hypothesis was true, of getting an event this extreme? And if that probability is very low, then maybe that's an indication that our hypothesis that the 50% is correct is not right. So, at any rate, we'll talk about p-values later. Well, I hope we'll get to talking about p-values later. But I just wanted to mention that that's where the intuition behind this calculation is coming from. Right now, we're only using it as an illustration of plugging into the binomial formula. but I wanted to foreshadow kind of an important statistical technique. And then here in this page is the likelihood associated with P for this particular binomial experiment, if we're willing to model births as if they were binomial. And so here you can see, 0.5 is in the 1/16th likelihood, but not in the 1/8th likelihood. And then you can see, that this likelihood is far more peaked around 7/8, or it reaches its maximum at 7/8, and then the curvature of it sort of gives you a sense of the relative evidence for the collection of possible values of P. So that's the binomial distribution. Let's talk about the most famous of all distributions, and probably the most handy of all distributions is the so-called normal or Gaussian distribution. The term Gaussian comes from the great mathematician Gauss. And it's kind of interesting to note, Gauss didn't invent the normal distribution. The invention of the normal distribution is kind of a debated topic. For example, Bernoulli had used something not unlike the Gaussian distribution as a probabilistic inequality, not formalizing it as a density. If you're interested in this, the book by Stephen Stigler on the history of statistics actually has a nice summary of exactly where and when and who came up with the Gaussian distribution. But it's clear that Gauss was instrumental in the early development and use of the Gaussian distribution. So a random variable is said to follow a normal or Gaussian distribution with parameters mu and sigma squared if the density looks like this: 2 pi sigma squared to the minus 1/2 e to the negative x minus mu squared over 2 sigma squared. And so this density, it looks like a bell, and it's centered at mu, and sigma squared sort of controls how flat or peaked it is. And so it turns out that the mu is exactly the mean distribution, and sigma squared is exactly the variance of this distribution. So you only need two parameters, a shift parameter and a scale parameter, to characterize a normal distribution. So we might write that x is this little squiggle, then n mu sigma squared, as just sort of shorthand for saying that a random variable follows a normal distribution with mean mu and variance sigma squared. And in fact, one instance of the normal distribution is sort of the kind of root instance from which all the others are sort of derived, and that's when mu equals 0 and sigma equals 1. And so we would call that the standard normal distribution. It's centered at 0 and its variance is 1. And so all other normal distributions are simple shifts and rescaling of the standard normal distribution. But then again, you could pick a different root, maybe mu equal 5 and sigma equal 2, but it wouldn't be quite as convenient. You could still get every other distribution from that one by shifting and scaling appropriately, but it wouldn't be as convenient. This is the most convenient way to define a sort of root of the normal distribution. The standard normal density is so common that we often reserve a Greek letter for it. So the lowercase phi we usually use for the normal density, and the uppercase phi we would use for the normal distribution function. And standard normal random variables are often labeled with a z, and you sometimes will even hear introductory statistics textbooks and so on refer to them as z variables or z distributed or something like that, and that's because this notation has become so common. Here's the normal distribution. It looks like a bell. That's how it gets its name, the bell-shaped curve. And sort of here I've drawn reference lines at 1 standard deviation, 2 standard deviations, and 3 standard deviations, 1 above and negatives being below and positives being above. Now again here, so the 1, right, because this is a standard normal distribution, right, the 1 represents 1 standard deviation away from the mean. Here the mean is 0. 1 is 1 standard deviation away from the mean. 2 is 2 standard deviations away from the mean. And 3 is 3 standard deviations away from the mean. Instead of thinking of these numbers as just z values on the denominator, if we think about them in the units of the original data, right, and this representing 1 standard deviation from the mean, 2 standard deviations from the mean, and 3 standard deviations from the mean, it doesn't matter whether we're talking about a standard normal or a non-standard normal, they all are going to follow the same rules. So about 68% of the distribution is going to lie within 1 standard deviation, about 95% is going to lie within 2 standard deviations, i.e. between -2 and +2, and about almost all of the distribution, about 99% of it's going to lie within 3 standard deviations. We can get from a non-standard normal to a standard normal very easily. So if X is normal with mean mu and variance sigma squared, then Z equal to X minus mu over sigma is in fact standard normal. Now, you could at least, given the information from this class, check immediately that Z has the right mean and variance. So if you take the expected value of Z, you get the expected value of X minus mu divided by sigma. You can pull the sigma out, and then you have expected value of X minus mu, which is just 0, because that's expected value of X minus expected value of mu. Mu is not random, so that's just mu. And mu is defined as expected value of X, so that's just 0. Then the same thing with the variance. If you take the variance of Z, you get the variance of X minus mu divided by sigma, right? So if we pull the sigma out of the variance, it becomes a sigma squared, and we have variance X minus mu. And we learned a rule with variances that if we shift a random variable by a constant, say in this case subtracting off mu, it doesn't change the variance at all, so we get variance of X divided by sigma squared. Variance of X is sigma squared, so we get sigma squared divided by sigma squared, which is 1. So at the bare minimum, we can check that Z has mean 0 and variance 1. By the way, there was nothing intrinsic to the normal distribution that occurred in that calculation, right? So we've also just learned an interesting fact, which is that take any random variable, subtract off its population mean, and divide by its standard deviation, and the result is a random variable that has mean 0 and variance 1. In this case, in addition, if X happens to be normal, then Z also happens to be normal. Similarly, we can just take this equation where Z equals X minus mu over sigma, and we can multiply by sigma and then add the mu and get that if we were to take a standard normal, say Z, scale it by sigma, and then shift it by mu, then we wind up with a non-standard normal. The top calculation goes from a non-standard normal and converts it into a standard normal, and the bottom equation starts with a non-standard normal and converts it into a normal. Another interesting fact is that the non-standard normal density can just be obtained as a plugging into the standard normal density. So if you take the standard normal density, phi, and instead of just plugging in Z to it, say, you plug in X minus mu over sigma, and then divide the whole thing by sigma, then that is exactly the non-standard normal density. And this is a kind of a way to generate, just kind of as an interesting aside. Here, mu is a shift parameter. So all mu does is shifts the distribution to the left or the right? Just like whenever you subtract a constant from an argument in a mathematical function, it's just moving the function to the left and the right. And then sigma is a scale factor. And so basically, whenever you take a kernel density, some density, I guess it works for any density, but it makes most sense to do it with a density with mean 0 and variance 1. And then you create a new family where you're plugging in X minus mu over sigma and then divide the density by sigma, you wind up with a new family of densities that now have mean mu and variance sigma squared. So this is kind of an interesting way of taking a root density with mean 0 and variance 1, and then creating a whole family of densities that have mean mu and variance sigma squared. They're usually called location scale families. At any rate, we're only interested in this case in the normal distribution, and this formula right here is exactly how you can go from the standard normal density and use it to create a non-standard normal density by plugging into its formula. Let's just talk about some basic facts about the normal distribution that you should memorize. So about 68%, 95%, and 99% of the normal density lies within 1, 2, and 3 standard deviations of the mean, respectively. And it's symmetric about mu. So, for example, take 1 standard deviation, about 34%, 1/2 of 68%, lies from within 1 standard deviation on the positive side, and about 34% lies within 1 standard deviation below the mean. So each of these numbers split equally to above the mean versus below the mean. And then there's certain quantiles of the normal distribution that are kind of common to have memorized. So negative 1.28, negative 1.645, negative 1.96, and negative 2.33 are the 10th, 5th, 2.5th, and 1st percentiles of the standard normal distribution. And then again, by symmetry, so if we just flip it around, right? So if negative 1.28 is the 10th percentile, then 1.28 has to be the 90th percentile. So by symmetry, 1.28, 1.645, 1.96, 2.33 are the 90th, 95th, 97.5th, and 99th percentile of the standard normal distribution. One in specific I want to point out that you really need to memorize is 1.96. The reason it's useful is it's the point so that if you take negative 1.96 and positive 1.96, the probability of lying outside of that range, right, below negative 1.96 or above positive 1.96, well, that's 5%. So 2.5% below it and 2.5% above it. So that's 5%. So the probability of lying between 1.96, negative 1.96, and positive 1.96 is 95%. And so anyway, it's used to do things like create confidence intervals and these other entities that are very useful in statistics, and people have kind of stuck with 95% as a reasonable benchmark for confidence intervals, and 5% is a reasonable cutoff for a statistical test. And if you're doing two-sided, you need to account for both sides, and so you use 1.96. And then the other fact is that 1.96 is close enough to 2 that we just round up. So a lot of times things like confidence intervals, you might hear people talking about, well, just add and subtract 2 standard errors. They're getting that 2 from this 1.96 right here. So anyway, that one in specific you should memorize, but you should probably just memorize all of them. Let's go through some simple examples. So we'll go through 2, and you should just be able to do lots of these after I go through 2. So let's take an example. What's the 95th percentile of a normal distribution with mean mu and variance sigma squared? So recall, what do we want to solve for if we want a percentile? Well, we want the point x naught so that the probability that a random variable from that distribution x being less than or equal to x naught turns out to be 95% or 0.95. Okay? And so, it's kind of hard to work with non-standard normals. So the probability that x being less than or equal to x naught is 0.95. Well, why don't we subtract off mu from both sides of this equation and divide by sigma from both sides of this equation. And on the left-hand side of this inequality, x minus mu over sigma, well, that's just a z random variable. Now, a standard normal random variable. So the probability that x is less than or equal to x naught is the same as the probability that a standard normal is less than or equal to x naught minus mu over sigma, and we want that to be 0.95. Well, if you go back to my previous slide, 0.95, 95th percentile of the standard normal is 1.645. So we just need this number, x minus mu over sigma, to be equal to 1.645 to make this equation work. And so let's just set it equal to 1.645, right? And then solve for x naught. So we get x naught equals mu plus sigma times 1.645. So now you could ask lots of questions with specific values of mu and sigma, but you'll wind up with the same exact calculation. And here, in fact, we used 1.645 because we wanted the 95th percentile, but in general, x naught's going to be equal to mu plus sigma z naught, where z naught is the appropriate standard normal quantile that you want. And then you can just get them very easily. The other thing I would mention too is you should be able to do these calculations more than anything, just so you've kind of internalized what quantiles from distributions are and how to sort of go back and forth between standard and non-standard normals and the kind of ideas of location, scale, densities, and that sort of thing. In reality and practice, it's pretty easy to get these quantiles because, for example, in R, you would just type in Q norm, 0.95, and then give it a mean and a variance. Or if you did Q norm 0.95 without a mean and a variance, it'll return 1.645, and you can do the remainder of the calculation yourself. But even that's a little bit obnoxious, so you can just plug in a mu and a sigma. So these calculations aren't so necessary from a practical point of view. Even very rudimentary calculators will give you normal quantiles, non-standard normal quantiles. the hope is that you'll kind of understand, the probability manipulations. You'll understand, what a quantile means. You'll understand, what the goals of these problems are. And you'll understand sort of how to go backwards between a standard and non-standard normal. That's kind of what we're going for here. It's kind of clear. I think everyone agrees that you can very easily just look these things up without having to bother with any of these calculations. Let's go with another easy calculation. What's the probability that a normal mu comma sigma squared random variable is 2 standard deviations above the mean? So in other words, we want to know the probability that x is greater than mu plus 2 sigma. Well, again, do the same trick where we subtract off mu and sigma from both sides, and we just get the answer that that's the probability that a standard normal is bigger than 2. And that's about 2.5%. And so you can see the kind of rule here. If you want to know the probability that a random variable is bigger than any specific number, or smaller than any specific number, or between any two numbers, instead of take those numbers and convert them into standard deviations from the mean, right? And that can, of course, be fractional. It could be 1.12 standard deviations from the mean or whatever. And the way you do that is by subtracting off mu and dividing by sigma, and then revert that calculation to a standard normal calculation. So if you wanted to know what's the probability that a random variable is bigger than, say, let's say 3.1, just to pick out a random complicated sounding number. Let's suppose you're talking about the height of a kid and you want to, say what's the probability of being taller than 3.1 feet. What you would need is the population mean mu and the standard deviation sigma. Take 3.1, subtract off mu, divide by sigma. Now you've just converted that quantity, 3.1, which is in feet, right, to standard deviation units. And then you can just do the remainder of the calculation using the standard normal. So I would hope that you could kind of familiarize yourself with these calculations. And I recognize that, in a sense, they're kind of ridiculous to do because you can get them from the computer so quickly. And we'll give you the R code that you need to do these calculations very quickly on the computer. But I think it's actually worth doing them by hand some, just to get used to working with densities, to get used to what these calculations refer to. So let me just catalog some properties of the normal distribution. A lot is known about the normal distribution. And so I'll outline some of the simpler stuff, and some of the stuff, the letter points, we probably won't get to in this class, but I thought I'd just at least say. So anyway, the normal distribution is symmetric and it's peaked about its mean, which means that the population mean associated with this normal distribution, the median, and the mode are all equal right at that peak. A constant times a normally distributed random variable is also normally distributed. And you can tell me what happens to the mean and the variance if, say, x is a normal random variable. What distribution does a times x have if I'm going to tell you that it's normal? What's the resulting mean and variance? It turns out that sums of normally distributed random variables are again normally distributed. And this is true regardless of the dependent structure of the data. So if the random variables are jointly normally distributed, it's important that they're jointly normally distributed. They could be independent, they could not be independent, but they need to be jointly normally distributed. The sums or any linear function of the normal random variables turns out to be normally distributed. And again, you can calculate the mean and the variance. Sample means of normally distributed random variables are again normally distributed. Again, this is true regardless of whether or not they're jointly normal and possibly dependent, or if they're simply a bunch of independent normal random variables. This is true of sample means. However, let me just jump to point 7. It also turns out that if you have independent, identically distributed observations, properly normalized sample means, their distribution will look like a Gaussian distribution, not entirely, but pretty much regardless of the underlying distribution that the data comes from. So take as an example, if you roll a die and look at what the distribution of a die roll looks like, it doesn't look very Gaussian. It looks like a uniform distribution on the numbers 1 to 6. Now take a die roll it 10 times, take the average, and then repeat that process over and over again and think about what's the distribution of this average of die rolls. Well, it turns out it'll look quite Gaussian. It'll look very normal. At any rate, that's the rule, is that random variables properly normalized with some conditions that we're probably going to gloss over will limit to a normal distribution. And that's how the normal distribution became the sort of Swiss Army knife of distributions, is that pretty much anything you can relate back to a mean of independent things tends to look normalish in distribution. And mathematically, formally, if they're independent and identically distributed you normalize the mean in the correct way, then you get exactly a standard normal distribution. That is an incredibly useful result. It's a very historically important result called the central limit theorem. So let's see, back to point 5. If you take a standard normal and square it, you wind up with something that's called a chi-squared distribution. You might have heard of that before. And if you take a standard or non-standard normally distributed random variable and exponentiate it, take e to the x, where x is normal, then you wind up with something that's log normal. Log normal is kind of a bit of a pain in the butt in terms of its name. A log normal means take the log of a log normal and it becomes normal. It doesn't mean the log of a normal random variable. It's a little annoying fact, right? And you can't log a normal random variable, by the way, because there's a non-zero probability that it's negative and you can't take the log of a negative number. The name makes it sound like a log normal is the log of a normal. It's not. Log normal means take the log of me and then I'm normal. Okay, let's talk about ML properties associated with normal random variables. If you have a bunch of IID normal mu sigma squared random variables, and let's assume you know the variance, so let's ignore the variance for the moment, then the likelihood associated with mu is written out right here. You just take the product of the likelihoods for each of the individual observations. And so you wind up with 2 pi sigma squared to the minus 1/2 e to the negative xi minus mu squared over 2 sigma squared. If you move that product into the exponent, you get minus summation I equal 1 to n xi minus mu squared over 2 sigma squared. Remember, we're assuming that the variance is known. So the 2 pi sigma squared to the minus n over 2 that you would have gotten, we can just throw that out, right? Because remember, the likelihood doesn't care about factors of proportionality that don't depend on mu, in this case, because mu is the parameter we're interested in. By the way, this little symbol right here, this proportion to symbol is what I mean. That means I dropped out things, it's proportional to, I dropped out things that are not related to mu. And I'll try and use that symbol carefully where it's contextually obvious what I mean, what variable I'm considering important. Okay, so let's just expand out this square and you get summation xi squared over 2 sigma squared plus mu summation xi over sigma squared minus n mu squared over 2 sigma squared. Now, this first term, negative summation xi squared over 2 sigma squared, again, that doesn't depend on mu. So we can just throw it out, right? It's e to that power times e to the latter 2 powers. So that first part is a multiplicative factor that we can just chuck. Then the other thing here is it's a little annoying to write summation xi. Why don't we write that as nx bar, right? Because if you take x bar, the sample average, and multiply it by n, you get the sum. Okay, so the likelihood works out to be mu n x bar over sigma squared minus n mu squared over 2 sigma squared. So that's the likelihood. Let's ask ourselves, what's the ML estimate for mu when sigma squared is known? Well, as we almost always do, the likelihood's kind of annoying to work with, so why don't we work with the log likelihood? We take the log from the previous page, and we get mu n x bar sigma squared minus n mu squared over 2 sigma squared. If you differentiate this with respect to mu, you wind up with this equation right here, which is clearly solved at x bar equal to mu. And so what it tells us is that x bar is the ML estimate of mu. So if your data is normally distributed, your estimate of the population mean is the sample mean. That makes a lot of sense. We would hope that the result would kind of work out that way. But also notice, because this calculation didn't depend on sigma, This is also the ML estimate when sigma is unknown. It's not just the ML estimate when sigma is known. So we know what our ML estimate of mu is. Let me just tell you what the ML estimate for sigma squared is. The ML estimate for sigma squared works out to be summation xi minus x bar squared over n. And you might recognize this as the sample variance, but instead of our standard trick of dividing by n minus 1, we're now dividing by n, which is a little frustrating that there's this kind of mixed message that the maximum likelihood estimate for sigma squared is the so-called biased estimate of the variance rather than the unbiased one where you divide by n minus 1. Now notice as n increases, this is irrelevant, right? The factor that disputes the two estimates is n minus 1 over n, and that factor goes to 1 as n gets larger and larger. So I've had several colleagues tell me that they would actually just prefer this estimate, this maximum likelihood estimate, and their argument is something along the lines of, well, the n minus 1 estimate is unbiased, but this one has a lower variance. And what they mean is, this is the biased version of the sample variance. It's only a function of random variables, so it itself is a random variable. And as a random variable, it has a mean and a variance. The fact that its mean is not exactly sigma squared means that it's biased, but it has a variance, and its variance is slightly smaller than the variance of the unbiased version of the sample variance. And so this is an example that pops up all the time in statistics, that you can trade bias versus variance. In this case, one variance estimate is slightly biased, but will give you a lower variance. Another one is unbiased, but the variance estimate itself has a larger variance. And it's very frequent in statistics that you have this kind of trade-off. You can pick one. As you increase the bias, you tend to decrease the variance and vice versa. So the other thing I wanted to mention was here we've kind of separated out inference for mu and inference for sigma. If you wanted to do kind of full likelihood inference, then you have exactly a bivariate likelihood, a likelihood that depends on mu and sigma. And it's a little bit difficult to visualize, but it is just a surface, right, where you have mu on one axis, sigma on another axis, and the likelihood on the vertical axis. Then it would just be a likelihood surface instead of a likelihood function. And it's a little bit hard to visualize these kind of 3D looking things. So there are methods for getting rid of sigma and looking at just a likelihood associated with mu, and getting rid of mu and looking at a likelihood just for sigma. And later on, we'll discuss methods for them. But for the time being, it's not terribly important. What I would hope you would remember is that if you assume that your data is normally distributed, then, we gave you the likelihood for mu if you assume sigma was known. We calculated that the ML estimate of mu was in fact x bar, and that the ML estimate of sigma squared was, pretty much the sample variance, off by a little bit from the standard sample variance, but pretty much the sample variance. And then, the ML estimate of sigma, not sigma squared, but of sigma is just the square root of our estimate for ML estimate for sigma squared. Well, that's the end of our whirlwind tour of probably the two most important distributions. There are some other ones that we'll cover later. Next lecture, we're going to travel to a place called Asymptopia. And everything's much nicer in Asymptopia, and so I think you'll quite like it there.